Imagine you're driving down the highway at 80 miles an hour. You suddenly see a massive concrete wall ahead, so you just slam on the brakes with everything you have.
Like full panic mode.
Right, full panic. But instead of slowing down, your car instantly accelerates to 1,000,000 miles an hour and just launches into the sky.
Which is, completely absurd.
It's completely absurd, that absolute defiance of logic, that complete shattering of what we think we know about how physical objects behave. That is exactly what is happening to our entire universe right now.
Yeah, it really is the definition of a paradigm shift. I mean, we live in a cosmos that is actively breaking the foundational rules we thought governed it.
It's just wild. So welcome to the deep dive, everyone. Today, we're taking you into, honestly, the single strangest observation modern science has ever made.
Without a doubt.
The universe isn't just expanding, it's getting bigger, faster, and faster. And to be completely transparent with you up front, nobody has a definitive answer for why it's happening.
No, we really don't.
The source material we're looking at today zeroes in on this cosmic mystery, which scientists call dark energy. But a key takeaway from our readings is that dark energy isn't an answer. It's just a placeholder name for a mystery that makes up most of our reality.
Exactly. I mean, calling it dark energy implies we understand it, right? The way we understand electrical energy or thermal energy, we don't.
Not even a little bit.
But to fully grasp why this acceleration is causing such a crisis in modern physics, we first need to trace the steps back to what astronomers firmly believed was the undisputed truth.
Right, the old baseline. So before we get to the shock of the acceleration, let's look at why everyone assumed the universe was slowing down. Why were they so confident?
Well, the foundation of that confidence goes all the way back to the 1920s with Edwin Hubble.
The telescope guy.
The very same. He observed that galaxies are, on average, receding from one another. So the universe is expanding. And if you rewind that expansion, logically, everything must have been packed tightly together in the past.
Which gives us the Big Bang.
Exactly, that initial outward push.
I want to make sure we're visualizing this correctly for you listening, because the sources use an analogy that really helps. They describe it like a loaf of raisin bread baking in an oven.
It's a classic analogy for a reason.
Yeah, so the dough is space itself, and the raisins are the galaxies. As the dough bakes and swells, the raisins just get further apart.
That's a perfect way to picture it, because the galaxies aren't firing thrusters and flying through space.
Right.
The space between them is physically stretching, and that carries them along.
Okay, so I'm following the expanding dough. But here is my confusion with the classical model. The universe is filled with matter, right?
Absolutely.
Galaxies, dust clouds, stars, planets. And all of that matter has mass. And mass exerts gravity. So if you have all these objects pulling on each other gravitationally across the universe, shouldn't that mutual attraction counteract the stretching?
You would assume that, yes.
I mean, I'd assume gravity would act like a massive brake on the entire system.
And so did every prominent physicist for decades. It's completely logical. If you have the initial explosive expansion from the Big Bang pushing outward, but you have the collective gravity of all the matter in the universe pulling inward.
The expansion has to lose momentum.
It has to. So the scientific community wasn't debating if the expansion was decelerating.
Oh, they assumed it was a given?
Totally a given. They were only debating the ultimate outcome of that deceleration.
Right, like how the story ends.
Yeah. Option one was that there is enough matter in the universe that gravity eventually wins, stops the expansion completely, and pulls everything back together in a big crunch.
The ultimate collapse. And option two.
Option two was that there isn't quite enough matter to stop it entirely, so the universe just coasts outward forever, continually slowing down but never fully stopping.
Okay, so if the math was so flawless and literally everyone agreed gravity was putting on the brakes, why did anyone even bother checking?
Well, because scientists want to know the exact parameters of the reality they live in,
Fair enough.
So in the 1990s, two independent teams of astronomers wanted to settle the debate. They wanted to measure the precise rate of deceleration to figure out which fate awaited us, the big crunch or the infinite coast.
Right.
To do that, they needed a way to measure extreme distances across the universe. So they used something called a Type Ia supernova.
Let me stop you there, because the sources call that a standard candle. What exactly makes an exploding star standard?
Okay, so a Type Ia supernova starts with a white dwarf. That's the super-dense leftover core of a dead star.
Just a glowing ember of a star.
Right, and sometimes a white dwarf will siphon gas off a nearby companion star.
Yeah.
As it steals this material, it gets heavier and heavier until it hits a very specific mathematical mass limit.
Oh, like a tripwire.
Exactly as a tripwire. When it crosses that exact threshold, it triggers a runaway nuclear fusion reaction and detonates.
Wow.
Because they always explode at that precise mass limit, the resulting explosion peaks at almost exactly the same true intrinsic brightness every single time.
Ah, I see. So it's like having a literal candle in a dark field.
Exactly.
If you know exactly how bright a candle is up close, and you walk, say, a mile away, you can measure how dim it looks to your eye to calculate the exact distance.
That's the principle, yeah.
So because we know the true brightness of these supernovae, measuring their apparent brightness from Earth tells us exactly how far away they are.
Precisely. But just knowing the distance isn't enough to track the expansion.
Yeah.
We also have to know how fast that particular piece of space is moving away from us.
Okay, and how do we figure that out? The sources talk about the universe stretching their light, but I'm not clear on the mechanics of that.
Think of light as a wave, like ripples on a pond.
Okay.
As light from that distant supernova travels toward Earth across billions of light years, the space it's traveling through is constantly expanding.
The dough is baking.
Right. As space stretches, the light wave itself physically gets stretched out. The wavelength gets longer.
And longer wavelengths mean what?
In physics, longer wavelengths of visible light appear red to our eyes. This phenomenon is called redshift.
So the more the light is stretched out, the more red it looks to our telescopes.
Yes.
And that tells us how much the universe expanded while that light was in transit.
You've got it. Because looking far out into space means looking back in time, since light takes billions of years to reach us. These teams could look at supernovae at different distances and map out the universe's expansion speed across different eras.
Oh, they were building a historical timeline of the cosmos.
Yes, exactly. And they fully expected the timeline to show that the expansion was much faster in the deep past and slower recently.
Because gravity was pumping the brakes?
Right. But in 1998, they looked at the final data, and the results were completely backward.
Backward, meaning the supernovae were fainter than they should have been.
Fainter, which means further away.
Which means?
The expansion of the universe hadn't been slowing down at all. When they plotted the data points, they saw that for the first several billion years of the universe's life, the expansion did slow down.
So gravity was doing its job initially.
It was. But roughly 5 billion years ago, the universe shifted gears. The deceleration stopped, the universe hit the gas pedal, and the expansion started accelerating outward.
That is completely wild. I mean, I can just imagine the teams looking at their computer screens thinking they had a software bug.
Oh, they spent months trying to find the error in their own work. They tested every possible interference, like maybe intergalactic dust was dimming the supernovae, or maybe they calibrated their sensors wrong.
But the data held up.
It held up. The universe is speeding up. It fundamentally broke our understanding of cosmology. And the leaders of those teams, they were actually jointly awarded the Nobel Prize in Physics in 2011 for the discovery.
Okay, so if we accept the observation that the universe hit the accelerator about 5 billion years ago, the immediate burning question has to be, what's the fuel? What is the engine providing the repulsive force to physically push the fabric of space apart?
Yeah, that is the multi-billion-dollar question right there. Yeah. The leading theoretical candidate we have, which is heavily featured in our source text, is called vacuum energy.
Vacuum energy.
Yes, and this requires us to fundamentally rethink what empty means. In classical physics, a vacuum is just a void with nothing in it.
Just empty space.
Right. But in modern quantum mechanics, empty space isn't truly empty. It's a boiling, seething soup of virtual particles popping into and out of existence constantly.
Okay, that sounds like sci-fi.
It does. But this activity means that space itself has an inherent baseline energy.
Hold on, I need to stop you there because I am genuinely getting tripped up by this.
Yeah.
The text uses an analogy of a box of gas to explain this.
Yep.
So if I have a 1 cubic foot box filled with gas and I suddenly expand that box to 2 cubic feet, the gas inside spreads out to fill the new volume.
Right, it dilutes.
The density drops. Are you saying vacuum energy doesn't do that?
That's exactly what I'm saying. Normal matter dilutes when you expand the volume. Vacuum energy, though, is a property of space itself.
Okay.
So if every cubic foot of space contains a specific amount of vacuum energy, and you suddenly create a second cubic foot of space, you don't dilute the energy.
Because you just made more space.
Exactly. Which means you now have twice as much vacuum energy.
That completely breaks my brain. It violates every intuitive rule of how physical stuff is supposed to behave.
It is highly counterintuitive. But it elegantly explains the timeline the astronomers found in 1998. It creates a cosmic feedback loop.
Let me see if I can trace the loop here. The universe expands, which creates more space.
Yes?
Because there is more space, there is more vacuum energy. That extra energy pushes the universe apart even faster.
Which creates even more space, which creates even more vacuum energy, which pushes even harder.
So it's a runaway train. And meanwhile, all the normal matter, the galaxies, the stars, the stuff exerting inward gravity, that is acting like the gas in the box.
Right. It's diluting.
As the universe gets bigger, the matter gets spread thinner and thinner, so its collective gravitational pull just gets weaker.
That's the mechanism. So for the first 8 billion years after the Big Bang, matter was dense enough that its gravity overpowered the push of the vacuum energy, slowing the expansion down.
Oh, I see.
But as the universe kept growing, matter diluted and vacuum energy accumulated. Roughly 5 billion years ago, the outward push finally eclipsed the inward pull. The cosmic scale tipped, and the universe began accelerating.
You know, there's a detail in the reading that I find just incredibly ironic, this idea that space has a built-in outward pressure. It wasn't cooked up in the 1990s to explain this acceleration.
Not at all.
Albert Einstein actually invented it nearly a century earlier.
He did, yeah. Back in 1917, while he was finalizing his general theory of relativity. Einstein's original equations actually suggested that the universe must be dynamic. Like, it had to be either expanding or collapsing under its own gravity.
But at the time...
Right. At the time, the entire scientific establishment believed the universe was static and eternal. It didn't move.
So rather than trusting his own math, Einstein added a brand new variable to his equations to force them to be static.
Yes. He called it the cosmological constant.
A mathematical anti-gravity.
Exactly. It was a repulsive force of space itself, calibrated perfectly to balance out the inward pull of matter.
So he introduced a fudge factor to match the prevailing bias of his era?
He did. But 12 years later, Edwin Hubble discovered the universe was actually expanding. The static universe was a total myth.
Oops.
Yeah, Einstein realized he hadn't needed to alter his equations at all, and he famously referred to the cosmological constant as his greatest blunder.
Yet, fast forward to today, and physicists are pulling Einstein's blunder right out of the trash can. I mean, when we try to mathematically describe the dark energy pushing our universe apart, the cosmological constant is the simplest, most elegant fit. He was right for the completely wrong reasons.
It's a fascinating quirk of scientific history, isn't it? But we have to be very careful not to just slap Einstein's name on it and call the mystery solved.
Where's that?
Because when we actually try to combine Einstein's constant with our modern quantum mechanics, the entire theoretical framework just collapses.
I'm really glad you brought this up because the sources dedicate a significant amount of time to this problem. We know dark energy is there. We can measure its effects. Let's look at the actual inventory of the universe today. According to the measurements, dark energy accounts for about 68% of everything in the cosmos.
It is the overwhelmingly dominant ingredient of reality.
68%. And dark matter, which is the invisible material providing extra gravity to hold galaxies together, that makes up roughly 27%. And ordinary, everyday matter, everything we can see, every star, planet, tree, and person, accounts for a measly 5%.
Just 5%. It's wild to think about.
Okay, so if we can measure the universe at precisely 68% dark energy, 27% dark matter, 5% normal matter, why does the math collapse? What is the actual problem?
The problem arises when theorists try to calculate how much vacuum energy there should be, using the fundamental rules of quantum mechanics.
Yeah.
When they add up all the seething quantum fields that we know exist in empty space, they get a theoretical number for the cosmological constant.
Right.
Then they compare that theoretical prediction to the actual observed acceleration measured by our telescopes. The two numbers don't match.
Well, I mean, science deals with margins of error all the time, right? How far off are the theorists?
It is widely considered the single worst prediction in the history of physics.
Oh.
The quantum calculation is too high by a factor of 10 to the power of 120.
Wait, like a 1 with 120 zeros behind it?
Yes, 10 to the 120th power. It's an error so unfathomably massive that it really defies human comprehension.
That is, I mean, that's catastrophically wrong.
If the theory was correct, It predicts an energy density so intense that it would have ripped the universe apart completely before galaxies or atoms could even form.
So that's not a rounding error. That is a flashing red siren that our understanding of reality is fundamentally broken somewhere.
Definitely.
If quantum mechanics says the vacuum energy should be astronomically huge, but our telescopes say it's just strong enough to gently accelerate the universe, we are missing a major puzzle piece.
And this colossal mismatch is exactly why many physicists are actively exploring alternatives to Einstein's cosmological constant. Maybe dark energy isn't a constant fixed property of space at all.
Right. The source mentions a concept called quintessence. Could you explain how that differs from the cosmological constant?
Sure. So the cosmological constant assumes the energy density of a cubic foot of space is exactly the same today as it was 10 billion years ago and will be the same 10 billion years from now.
It's rigid.
Exactly. But quintessence proposes that dark energy is dynamic. It's an energy field permeating space that can change over time.
Oh, interesting.
It could slowly lose strength or gain strength, almost like a shifting cosmic weather pattern.
Or maybe the problem is even deeper. I saw one suggestion in the reading that maybe Einstein's theory of general relativity, our core theory of gravity, is just incomplete.
That's another major possibility.
Because it works perfectly when we test it around our sun or black holes, but maybe on the grandest scale of the entire universe, gravity doesn't act the way we think it does.
All these hypotheses are on the table right now. But science requires evidence, and gathering that evidence requires mapping the cosmos with unprecedented precision.
Right?
This is why the European Space Agency recently launched the Euclid Space Telescope, and why massive ground-based projects like the Dark Energy Spectroscopic Instrument, or DSI, are currently operating.
How does drawing a map solve a quantum math problem?
By reconstructing the precise history of the universe's expansion. These telescopes are mapping the three-dimensional positions of billions of distant galaxies to trace exactly how the expansion rate has changed over the last 10 billion years.
Okay.
If dark energy is truly a cosmological constant, the timeline of acceleration will follow a very specific, rigid mathematical curve.
But if it's quintessence,
Yeah.
if the dark energy is shifting or drifting over time, the expansion curve will wobble.
Exactly. And a shifting field will leave a different imprint on the structure of the universe. In fact, some of the initial data releases from these mega surveys in the mid-2020s have shown faint, tantalizing hints that dark energy might actually be drifting.
Wait, really?
Yeah, the measurements are showing slight deviations from a perfect cosmological constant.
Wow. If that holds true, it would completely rewrite physics.
It would be a monumental paradigm shift. But I want to stress to you, the listener, that in science, extraordinary claims require extraordinary evidence. The statistical confidence isn't high enough yet to declare a revolution. We need more data, more observations over the next several years to know for sure.
Well, while we wait for Euclid and other observatories to deliver their final verdicts, I think we have to confront what this acceleration actually means for the deep future of the universe. The source paints a picture that is, frankly, chilling.
It is a very sobering reality. If dark energy remains dominant and the universe continues to accelerate its expansion forever, it dictates a very lonely fate for the cosmos.
Right now, we can look up and see hundreds of billions of galaxies. But as the universe expands faster and faster, the space between us and those distant galaxies is stretching.
Stretching faster every second.
And eventually that space will be stretching so rapidly that it actually exceeds the speed of light.
Which means the light from those distant galaxies will no longer be able to reach us. It's like trying to run up a down escalator that's moving faster than you can sprint.
You'll never reach the top.
You'll just never make progress.
So over billions and billions of years, those galaxies will just blink out of our observable universe. They will cross a cosmic horizon and vanish forever.
Vanish without a trace.
To an astronomer living 100 billion years from now, the night sky will be almost entirely black. They will only be able to see the stars of our own Milky Way, and maybe a few neighboring galaxies that were close enough for gravity to hold them together. Everything else will be gone.
They will have absolutely no observational evidence that a wider universe ever existed. The cosmic microwave background, the distant supernovae, all the clues that gave us the Big Bang Theory wiped clean.
Just erased. It makes you incredibly grateful that we happen to be living in the exact sliver of cosmic time where we can still see the evidence. We get to map the galaxies before they run away from us.
It is incredibly humbling. I mean, it reminds us that 68% of our universe was found completely by accident and defies explanation by our most successful theories.
Yeah.
And it's described by a term Einstein invented and disowned. Science is just an ongoing, beautifully unfinished project.
It really is. And as we wrap up today's deep dive, I want to leave you with one final thought to mull over. Building on this idea of the universe hiding its own history. We know the universe has been accelerating for the past 5 billion years, right? Slowly pulling the curtain shut on the cosmos.
Right.
We worry about future astronomers not being able to see what we see today. But consider this. What if there were magnificent, grand cosmic structures out there that have already been carried away? Are we, right now, looking up at a universe that has already been partially erased, long before human eyes even evolved to look at it? Something to think about the next time you look at the stars. Thanks for listening.